Okay, hi, this is Screencast 6.0, an introduction to the periodic table. Now, I don't want you to expect too much from this screencast because really I'll be just reading the text that is provided in this link itself. So, let's get started on an introduction to the periodic table. There's your standard periodic table right there. And as you know, there's about 120 elements in it, and they're shown there in the order that you normally see them. Now, you're aware of the organization, I'm sure. They're organized by increasing number of protons. Hydrogen has one, helium has two, etc. And you're probably aware that electrons reside in increasing energy following the Aufbau order. 2 in the first shell, 8 in the second shell, but divided into subshells, etc. So as we work our way in this infinite pattern, which I think is really cool, we see that a beautiful symmetry ensues, bringing us out to all the known elements that would be right there, about 118 elements, and well beyond into the new elements that have yet to be discovered. And in fact, they may or may not ever be discovered because there's just too many neutrons in their nuclei. Regardless, you can see that this is an infinite pattern, and you could continue. For example, element 242 would have an ending electron configuration of 6H22. Get it? So you can just continue this thing forever, which is kind of cool. Because of that, a nice way to organize the periodic table is by this extended form. This extended form can include additional blocks. And another nice thing about it is that the F block, which is right here, is no longer thrown in at the bottom of the periodic table. It follows in order. Well, mostly in order. S, P, D, F, and starting at element 121, which may show up someday, we have the G block. You can imagine that the H block would go there, etc., etc., going out 2, 6, 10, 14, 18, 22, and it's a neat pattern. The real shame of it is that the periodic table is not usually shown like this. This is a nice way to do it. You don't need to go on to new elements, but it would be nice. It would be even nicer if it could be made purely symmetric. You might consider what would happen if we threw this part over here, if the entire thing would become a perfect right triangle, showing the symmetry of the universe, if you will. In any event, this is the extended form of the periodic table. Although the electron configuration seems to be so beautiful, there does seem to be a lot of anomalies to it. A lot of places where it just does not follow that rule. Lots of exceptions. This normally has to do with wanting to get a full shell, I should say a subshell, at the expense of taking out another electron. But just suffice it to say that there's lots of exceptions to this, which is a bit of a shame in some respects. Or perhaps it's the sign of an underlying pattern that we haven't yet discovered. Because of that, many of the periodic tables you see will give you the electron configuration for every single element because there's so many anomalies. So that's something to be aware of as well. Finally, let's talk about a few more electron configuration limitations, and let's show you the naming system for the new elements. Okay, one thing about the Aufbau order is that you would think if you had an element like scandium, whose ending electron configuration 4s2 and then 3d1 implies that this might be the electron that gets lost when it forms an ion, but in fact it's not. In fact, it's an electron from here that gets lost, from the valence shell, when you form an ion, which is a little silly because it's so quick to come up with the valence electrons and just quickly say, oh, it's an electron in the fourth shell, that would be what's lost. What's the point of going out to all this detail when it gives you misinformation? You also get somewhat misinformed if you try to figure out how many bonding electrons will form for a simple system. Let's do carbon, for example. 4 valence electrons, spread them out, Hund's rule, 4 bonds. Life is good. That's a smiley face. But if you do out the electron configuration, I'm going to do it nice and big right on top here. For carbon, it's 1s2, 2s2, 2p2, one box for the s's. Everything's filled up. Opposite spins. Draw all three boxes for p, since it can hold 6 electrons. Spread them out. You would think it would form 2 bonds, but in fact it forms 4 bonds, not 2. And this does seem to be a little bit of a problem. People who know about this say, we hybridize it. Why do you hybridize it? Because this doesn't work, if you ask me. And so it's a little bit of a surprise. I should point out that one thing that it does very well is show that electrons fill up out of order, if you will. In other words, they don't go first shell, second shell, third shell, fourth shell, fifth shell. They go back into inner shells. The D block, the F block, the G block, when it gets discovered, all will. And as a result, the only valence electrons involved will always be S and P, and you can never have more than 8, which is kind of interesting. Temporary names. It's really a pretty simple system. They have a little way that they name the elements that have not yet been confirmed. Here's one right here. UUO. The U means 1. Un. The other U means 1 again. So that's 1, 1. And then the O, let's find it. There it is right there. Un octium, element 118. UBN, un bibium would be un for 1. Bib for 2, the B really, and then another B for another 2. This sounds to me like unbibium. That says element 120. I get 122. I think that's an error, actually. I think that is 122. I think 120 would be unbibnilium. Anyhow. There you go. So this is the naming system that they have for the periodic table for the elements that have not yet been discovered. This is Introduction to the Periodic Table screencast 6.0.